When working with micro-optical components, for example in such an automated production, it's often complicated to use conventional grippers. If you want to find out what we use instead, just stick around and we'll check it out. To handle micro-optical parts, we often use vacuum grippers. Although they might be better suited than mechanical grippers, they also have their challenges. And to have a closer look at this, let's go upstairs to the lab. So here we are in the lab. And to show you the challenges, Maya has prepared some experiments.
It's a simplified setup. What we can see here is a glass plate that represents our optical component and a picking tool that works with vacuum. And if we have enough vacuum, we are able to pick our component up.
And as you said, we need enough vacuum. So if I'm squashing the tube here and reducing the diameter, it can happen that it falls down.
Another challenge is that we not only want to pick our optical component up, but move it from one side to another side. And it could be, if our vacuum is not good enough, that our optical component loses its position.
Yeah. This looks quite easy. Now coming to the reality.
In reality, we are working with much smaller dimensions, as you can see here. And we want to pick up 5 of these optical components. And we want them to be aligned perfectly.
Right. And for that, here under the microscope, we have one of the tools. It's an actual tool from the automated production downstairs. And what you can see here in the front are 5 tiny little vacuum holes. They have a diameter of 200 micrometer or so. And the optical components, in this case, they are filters. They are placed on top next to each other in a very dense shape.
We also can see this here in our sketch. We have our filters here in green, and the mentioned 5 holes. This vacuum channel leads to a vacuum pump.
Yeah. Now, this looks quite nice and easy. If we now zoom in for the reality, the situation is a little bit different.
We can see contaminations and we can see scratches, and they can lead to secondary air. And because all of the holes are connected, the secondary air leads to a bad vacuum at all of these holes. If
we look a little bit closer, we can even see some particles or something inside the holes, right?
And with that, we are coming back to reducing the diameter, and the diameter can also be reduced by adhesive residues or particles, and this can lead to a bad vacuum.
Yeah, okay, I understand this. Due to the fact that we have a fully automated production line and it should work 24/7, this could be a problem. So we want to control the vacuum and make sure that the machine is running correctly. And luckily, you did your bachelor thesis at HUBER+SUHNER Cube Optics, and you have been working on a system to control this vacuum.
I think the most obvious solution would be to place a measurement head here, so that we can measure the vacuum of each hole. But in order to do this, we would have to interrupt our process, and that's something that we don't want. And because of this, we chose the solution of measuring in the bypass. We lose some information because we don't know the vacuum at these holes. Yeah. But I found in my bachelor thesis that we are still able to find some reference values for when no filter is laying in the system or on the system, and a reference value when all the filters are placed, and also the values in between. And like that, we are able to monitor our process and see if everything is fine.
Yeah. Perfect solution for the situation. We can do an in situ measurement and we can determine if the machine is running correctly or if we have to stop it and do some maintenance or something else. Okay, thanks for joining me in this video. Thank you for watching the video. I hope you learned something today, and see you in one of the next videos. Bye-bye.
Bye.